Today's topic is Fermi-Dirac statistics. Basic assumptions of Fermi-Dirac statistics are following. Number one, this statistics is applicable to those systems in which particles are identical and indistinguishable with spin equal to odd multiple of half. Spin is equal to odd multiple of half means spin S will be equal to 1 upon 2, 3 by 2, 5 by 2 and so on. It is multiplication to 1 by 2 by odd number 135. Odd number 135 multiplied by half. So this statistics, Fermi-Dirac statistics, is applicable to those particles which are identical and indistinguishable and have spin equal to odd multiple of half. These particles are known as fermions. Example is electrons, protons, etc. Electrons and protons both have spin half. So these are fermions. All the particles having spin S equal to 1 upon 2, 3 by 2, 5 by 2, which is odd multiple of half. All these particles are known as fermions and obey Fermi-Dirac statistics. Number two, since these particles are indistinguishable, we cannot distinguish between any two particles. Then by exchanging two particles, it is not TO2, it is TWO2. So by exchanging two particles, we do not get new microstate. If the particles were distinguishable, then by exchanging any two particles, we get new microstate. But now here, in Fermi-Dirac statistics, the particles are indistinguishable. We cannot distinguish between any two particles. So by exchanging two particles, we do not get any new microstate. Number three, minimum volume of phase cell in phase space is h cube. In phase space, smallest volume element is phase cell. It represents a microstate. So volume of phase cell in phase space is h cube, which is constant. H here is Planck's constant. So volume of phase cell in phase space is h cube, which is constant. So number of phase cells are fixed. Number four, these particles which are fermions, these particles obey Pauli's exclusion principle, according to which maximum number of particles in a phase cell is 1. Maximum number of particles in a microstate is 1. So in a phase cell or in a microstate, there can be either 0 particles or 1 particle. In a phase cell or in a microstate, number of particles is either 0 or 1. Maximum number of particles is 1. So this is the difference between Fermi-Dirac statistics and the previous statistics, which are Maxwell-Boltzmann and Bose-Einstein statistics. Now, number of particles, there is restriction in number of particles in a state. Here in a state, in a microstate, maximum number of particles is 1 because fermions obeys Pauli's exclusion principle. So these are the basic assumptions of Fermi-Dirac statistics. Now we will find the distribution law for Fermi-Dirac statistics. For this, we consider a system of capital N identical indistinguishable particles having a spin equal to odd multiple of half. Spin is odd multiple of half, that is half, 3 half, 5 half, 1 by 2, 3 by 2, 5 by 2 and so on. Example, a group of free electrons in metal. In metal there are large number of free electrons. Electrons have spin half, so these are fermions and obey Fermi-Dirac statistics. We distribute these capital N particles in phase cells in energy states such that in first cell number of particles are N1 and their energy is E1. In second cell number of particles are N2 and their energy is E2, and similarly for other cells. In general, number of particles in ith cell are Ni and their energy is Ei. It is not E1, it is Ei. With this, we also consider that there are Gi energy levels in ith energy state of energy Ei. So this Gi is known as degeneracy. Gi, which is number of energy states, number of energy levels of same energy Ei. It is known as degeneracy. So in ith cell, we have Gi energy levels all have same energy Ei. So we have degeneracy Gi. Since these particles obey Pauli's exclusion principle, maximum number of particles in a phase cell or in a microstate is 1. So in ith energy state of energy Ei, out of Gi levels, Ni levels will be filled. It is not fixed. Ni levels will be filled by Ni particles. In ith energy state of energy Ei, there are Gi levels, and we have to distribute Ni particles to these Gi energy levels. And in one energy level, we can put only one particle. So out of these Ni levels, out of these Gi levels, Ni levels are filled by Ni particles, one in each level. So Gi, there are Gi number of levels and number of particles is Ni. So out of these Gi levels, Ni levels are filled. Each level occupy one particle. Then remaining levels which are empty are Gi minus Ni. And remaining levels which are Gi minus Ni, these levels will be empty. From this distribution, we want to find most probable distribution. we want to find the condition of equilibrium, and equilibrium state is the most probable state which have maximum probability. Their thermodynamical probability of distribution of particles is given by this formula. Thermodynamic probability means number of microstates corresponding to a macrostate. So thermodynamic probability, which is number of microstates, is given by this formula. W equal to pi I factorial Gi upon factorial Ni into factorial Gi minus Ni. Pi I, this symbol represents the multiplication of several terms. For I equal to 1, we get one term, factorial G1 upon factorial N1 into factorial G1 minus N1. Similarly, for I equal to 2, we get other term. For I equal to 3, we have different term. And this pi I represents the multiplication of all these terms. Now, look at this formula for thermodynamic probability W. In denominator, we have factorial Ni and factorial Gi minus Ni. Total number of energy levels is Gi in ith state, and number of particles is Ni. So, Ni particles will be filled in Ni levels. So, first we have factorial Ni. Total number of particles is Ni. These Ni particles are in Ni levels, but levels are Gi. So, remaining empty levels are Gi minus Ni. So, second factorial is for factorial Gi minus Ni. Gi minus Ni here is number of empty energy levels. And in numerator, we have factorial of summation of these two terms which are in denominator, that are Ni and Gi minus Ni. So, in numerator we have factorial of Ni plus Gi minus Ni, that is Gi. So, this is the formula for thermodynamic probability W. It is equal to pi I factorial Gi upon factorial Ni into factorial Gi minus Ni. We write it as equation 1. Now, we have two more equations, for one for total number of particles capital N, and other is for total energy capital E. These are constants. Total number of particles capital N will be equal to N1 plus N2 plus N3, and we write it as summation Ni, and total energy is capital E, since N1 particles are such that energy of each particle is E1. So, N1 particles each have energy E1. So, their energy will be N1 E1, and we have N2 particles each having energy E2. So, their energy is N2 E2, and so on. So, total energy capital E of all these particles will be equal to N1 E1 plus N2 E2 plus N3 E3 and so on, and we write it as summation Ni Ei. This is equation 3, and these total number of particles capital N and total energy E, these two are constants. Now, we take log of this equation 1. Equation 1 is for W, that is thermodynamic probability, which is number of microstates. So, if we take log of this equation 1, we get log W. We write it as ln W. Ln is log for E base. So log W will be equal to summation I. This is the formula for W. Here we have symbol pi I. This symbol pi I represents the multiplication of different terms. But if we take log W, then this pi I will change to summation I. Summation I is summation, that is addition of different terms. Since log of A into B into C is log A plus log B plus log C, so this multiplication symbol will change to summation symbol. Now we have sum, addition of different terms. So we have summation I, and then if we take log, then in numerator we have factorial gi, so we write log factorial gi. Then in denominator we have these two factorials, factorial ni and factorial gi minus ni. Then log will be equal to minus log factorial ni and minus log factorial gi minus ni. Now we use Stirling formula. Stirling formula is for log factorial n. According to Stirling formula, log factorial n is n log n minus n. So log factorial gi will be equal to gi log gi minus gi. Then we have minus log factorial n. Here we also use Stirling formula. So log factorial ni will be equal to ni log ni minus ni. So we have these two terms, minus ni log ni plus ni. Then we have the last term, minus log factorial gi minus ni. So log factorial gi minus ni by using Stirling formula will becomes gi minus ni log gi minus ni minus gi minus ni. So we have these terms for log W by using Stirling formula. Here we have minus gi, here we have plus ni, and in last we have plus gi and minus ni. These four terms are cancelled. We have plus gi and minus gi, and we have plus ni and minus ni. These are cancelled out, and remaining terms will be gi log gi minus ni log ni and minus gi minus ni log gi minus ni. Now for most probable state, W and log W should be maximum. Most probable state is one which have maximum thermodynamic probability W. So for most probable state or for equilibrium state, W should be maximum or log W should be maximum, and condition for this is that its differentiation must be 0. So differentiation of log W must be equal to 0. So we write D, that is differentiation, and it is the value of log W, which is summation gi log gi minus ni log ni minus gi minus ni log gi minus ni, and it is equal to 0. Now we do the differentiation. D means differentiation. Differentiation of first term is 0 because gi is constant. So gi log gi, this first term is constant, its differentiation is 0. Now we have second term, which is minus ni log ni. Differentiation of this, we do differentiation of this term, then we use the formula of differentiation of first and second function. We assume that ni is first function and log ni is second function. So formula is first function differentiation of second plus second function differentiation of first. So first function is ni and differentiation of log ni, second function, is 1 upon ni dni. Then we have second function log ni and differentiation of first, differentiation of ni is dni. So we have these two terms. Similarly, we again use the formula here also. First function here is gi minus ni and second function is log gi minus ni. So first function is gi minus ni and differentiation of log gi minus ni is 1 upon gi minus ni into minus gi into minus dni. Differentiation of gi minus ni is minus dni. So this is first function differentiation of second. Then we have second function log gi minus ni and differentiation of first, differentiation of gi minus ni is minus dni, and this is equal to 0. First term is minus dni, ni and ni are cancelled out. First term is minus dni. Similarly, here we get the term plus dni. gi minus ni is cancelled out in numerator and denominator, and this term is plus dni. This plus dni and the first term is minus dni. These two terms are cancelled out. So remaining terms will be minus log ni dni and plus log gi minus ni dni. We have in first term minus log ni dni, second term is log gi minus ni dni. dni we can take common. Then we have inside the bracket minus log ni and plus log gi minus ni, and log a minus log b is log a upon b, so it becomes log gi minus ni upon ni. So we have summation log gi minus ni upon ni into dni equal to 0. We write this as equation 4. We have two more equations from these two equations, equations 2 and 3. Capital N, total number of particles is constant, so its differentiation dn will be 0. And total energy, capital E, is also constant, its differentiation dE will also be 0. So we get two more equations. One for dn equal to 0, this will give summation dni equal to 0. And dE equal to 0, this will give summation ei dni equal to 0. So we have these two equations. dn, which is summation dni, is equal to 0, equation 5. And dE, which is summation ei dni, it is equal to 0. This is equation 6. Now we combined these three equations, equations 4, 5 and 6. We now combine equation 4, 5 and 6 by using Lagrange's method of undetermined multiplication. So by using Lagrange's method of undetermined multipliers, we combine these three equations, equation 4, equation 5 and equation 6. For this, we multiply equation 5 by alpha. So this will become summation alpha dni equal to 0. We multiply in equation 6, we multiply by beta, so it becomes summation beta ei dni equal to 0. And then we subtract these equations from equation 4. So this is equation 4, summation log gi minus ni upon ni dni equal to 0. We subtract from this equation 5 by multiplying by alpha, and we subtract equation 6 also by multiplying by beta. Then we have summation I. dni is common in all these three equations. So we write dni in right side, and inside the bracket then remaining terms are log gi minus ni upon ni, this from equation 4, and from equation 5 we have minus alpha, because equation 5 is multiplied by alpha and we subtract it, and then we have minus beta ei, because we multiply by beta this equation 6, we have beta ei dni and subtract it also, then we get minus beta ei, and dni is common. So we get this equation summation log gi minus ni upon ni minus alpha minus beta ei into dni equal to 0. Ni is number of particle in ith cell, and dni is change in it. This change in number of particles is independent of I, number of state. So we must have this quantity inside the bracket equal to 0. So we get log gi minus ni upon ni minus alpha minus beta ei equal to 0, or log gi minus ni upon ni equal to alpha plus beta ei. Take exponential on both sides, then e to the power log x equal to x. So we have gi minus ni upon ni equal to e to the power alpha plus beta ei. Left hand side is equal to gi upon ni minus ni upon ni. So it is gi minus ni minus 1. Left hand side is gi upon ni minus 1, and it is equal to e to the power alpha plus beta ei. So gi upon ni is equal to e to the power alpha plus beta ei plus 1. If we invert this, then we get ni upon gi equal to 1 upon e to the power alpha plus beta ei plus 1, and this will give ni equal to gi upon e to the power alpha plus beta ei plus 1. This is Fermi Dirac distribution law. Ni equal to gi upon e to the power alpha plus beta ei plus 1. This is Fermi Dirac distribution law. Now we see the difference between Bose-Einstein and Fermi Dirac statistics. For Bose-Einstein statistics, spin of particles is 0 or integer. Spin is 0, 1, 2, 3, 4. Example is photon and phonon. These particles are known as bosons. For Fermi Dirac statistics, spin of particle is odd multiple of half. Spin s is equal to half, 3 half, 5 half. Example, electrons, protons having spin half. These particles are known as fermions. For Bose-Einstein statistics, there is no restriction on number of particles in one microstate or in one energy level. There can be any number of particles. But in Fermi Dirac statistics, these fermions obey Pauli's exclusion principle. So maximum number of particles in microstate is 1. Maximum number of particles in a energy level is 1. These are the difference between Bose-Einstein statistics and Fermi Dirac statistics. Both are quantum statistics. Now we look at the difference between these three statistics. First, Maxwell-Boltzmann statistics, which is classical statistics, and other two are quantum statistics, which are Bose-Einstein statistics and Fermi Dirac statistics. So we see the difference between these three statistics. For Maxwell-Boltzmann statistics, particles are identical and distinguishable, and for other two statistics, which are quantum statistics, particles are identical and indistinguishable. For Maxwell-Boltzmann statistics, spin whatever may be, For Bose-Einstein statistics, spin S will be 0, 1, 2, 3, 4, 0 or integer, and these particles are known as bosons. While for Fermi-Dirac statistics, spin must be odd multiple of half. Spin S must be equal to half, 3 half, 5 half. Such particles are known as fermions. Example of Maxwell-Boltzmann statistics is gas molecules. Example of Bose-Einstein statistics is photons, phonons. Example for Fermi-Dirac statistics are electrons, protons. Number 4, this is classical statistics. Maxwell-Boltzmann statistics is classical statistics in which minimum volume of phase cell is H0 cube, which is arbitrary. H0 is constant, it is not constant, it is such number which we can choose as small as possible. So number of phase cells can be increased as we wish. Minimum volume of phase cell is H0 cube, which is arbitrary. We can choose it as small as possible. So number of phase cells can be increased as we wish. But in quantum statistics, in both the Bose-Einstein and Fermi-Dirac statistics, this volume of phase cell is not H0 cube, it is H cube. So correct it here, it is H cube, and H is constant, which is Planck constant. So number of phase cells is fixed because H cube is constant. Volume of a phase cell is constant, then number of phase cells is constant, it is fixed. In Maxwell-Boltzmann statistics and Bose-Einstein statistics, both, there is no restriction on number of particles in a energy level or in a microstate. For both these two statistics, Maxwell-Boltzmann and Bose-Einstein statistics, there is no restriction on number of particles in microstates. In a microstate, number of particles may be 0, 1, 2, 3, 4, any number. But in Fermi-Dirac statistics, because these are fermions and obeys Pauli's exclusion principle, so here is restriction for number of particles in one energy level. According to Pauli's exclusion principle, maximum number of particles in one microstate is 1. This is most probable distribution for Maxwell-Boltzmann statistics, Ni equal to Gi upon e to the power alpha plus beta Ei. For Bose-Einstein statistics, this is Ni equal to Gi upon e to the power alpha plus beta Ei minus 1. And for Fermi-Dirac statistics, it is Ni equal to Gi upon e to the power alpha plus beta Ei plus 1. From these equations, if we find Ni upon Gi, it is known as occupation index, and we write it as Fei, function of Ei. So Ni upon Gi for Maxwell-Boltzmann statistics is, it is 1 upon e to the power alpha plus beta Ei. In denominator, it is not minus 1. It is only 1 upon e to the power alpha plus beta Ei for Maxwell-Boltzmann statistics. From this equation, Ni upon Gi is equal to 1 upon e to the power alpha plus beta Ei. It is Fei, known as occupation index. For Bose-Einstein statistics, Ni upon Gi is 1 upon e to the power alpha plus beta Ei minus 1. And for Fermi-Dirac statistics, Ni upon Gi occupation index is 1 upon e to the power alpha plus beta Ei plus 1. And these are the graphs for this function Fei, occupation index, versus Ei. This is for Maxwell-Boltzmann statistics for three different temperatures. This is for Bose-Einstein statistics for 3 different temperatures. And this is for Fermi-Dirac statistics for 3 different temperatures. limit of Bose-Einstein and Fermi-Dirac statistics for Maxwell-Boltzmann statistics. These are the three distribution formula for Maxwell-Boltzmann statistics. Ni equal to gi upon e to the power alpha plus beta ei. For Bose-Einstein statistics, we have Ni equal to gi upon e to the power alpha plus beta ei minus 1. And for Fermi-Dirac statistics, we have Ni equal to gi upon e to the power alpha plus beta ei plus 1. So difference is in denominator, in right hand side. The first term is same, e to the power alpha plus beta ei. In Maxwell-Boltzmann statistics, we have only e to the power alpha plus beta ei in denominator, in right hand side. For Bose-Einstein statistics, we have minus 1 with it. And for Fermi-Dirac statistics, we have plus 1 with it. But if Ni upon Gi is a large number, Ni upon Gi is very large number compared to 1, then if Ni upon Gi is a small number, Ni upon Gi is much less than 1, or Ni is much less than Gi. Ni is much less than Gi, so Ni upon Gi is much less than 1. Then from this equation we look at that if Ni upon Gi is much less than 1, then denominator should be large. So e to the power alpha plus beta ei must be much greater than 1. In this case, we can neglect this 1 in Bose-Einstein statistics and also in Fermi-Dirac statistics. And if this 1 is neglected in both these statistics, then these two statistics will change to this Maxwell-Boltzmann statistics. So the condition is Ni upon Gi is much less than 1 or Ni is much less than Gi, then e to the power alpha plus beta ei is much greater than 1. So in this case, neglecting 1 in comparison to e to the power alpha plus beta ei in Bose-Einstein and Fermi-Dirac statistics, these two distribution law convert in Maxwell-Boltzmann distribution law, that is Ni upon Gi equal to 1 upon e to the power alpha plus beta ei. So when Ni upon Gi is much less than 1, or when number of particles per quantum state is very small, Bose-Einstein and Fermi-Dirac statistics becomes equivalent to Maxwell-Boltzmann statistics. This happens at high temperature and low pressure. So at high temperature and low pressure, Bose-Einstein and Fermi-Dirac statistics loses their significance and becomes equivalent to Maxwell-Boltzmann statistics.